In the last lecture, we discussed about the compressive strength, tensile strength, and the factors affecting the test results. Today, we are going to discuss about stress strain curve and determination of modulus of elasticity for concrete. Why should we need this stress strain curve and modulus of elasticity and Poisson's ratio? Stress strain modulus of elasticity and Poisson's ratio. What's the need of these values? The need for these values is they are used to determine the deflection in the members. They are used to calculate the deflection and deformation in the structures. That is, these values will be used in structural analysis to determine the deflection and deformation in a structure. The stress strain curve for material is being classified into 4 types. First one is linear and elastic. This is the stress and this is strain. The stress strain curve for linear and elastic type will be a straight one, that is, during loading the stress and the strain increases simultaneously, and while unloading the strain and the stress will be in a linear pattern. Second, non-linear and elastic. Again, if we draw the stress strain curve, the stress and strain do not increase in a linear manner. There will be some variations, but when it is being removed, when the load is being removed, it returns to its original state. And the third is linear and non-elastic. The stress and strain will increases linearly during the loading, and while unloading it will not follow the same path. It follows a different path, that is, some permanent strain will be left. Fourth one is non-linear and non-elastic. During loading, the stress and strain varies non-linearly, and while removing also it will not follow a linear pattern. Some permanent strain will be left. Here it forms a loop-like structure, that is the hysteresis loop, that is during the cyclic loading it forms as in earthquake loading a hysteric loop will be formed here. And concrete belongs to non-linear and non-elastic type. Concrete belongs to this fourth category, that is non-linear and non-elastic type. For concrete, modulus of elasticity can be determined in different ways. Modulus of elasticity assume it to be the stress strain curve for a concrete. If suppose I determine, if suppose I choose this point and if I draw a tangent here, then it is termed as initial tangent modulus. But this initial tangent modulus will not give the exact modulus of elasticity of the concrete, since it gives the value only for low stress levels. So next I am choosing an arbitrary point somewhere here on the stress strain curve, and I am again drawing a tangent, and this is called as tangent modulus. Again here also the same problem arises, that is within the vicinity of this point alone I will be getting the appropriate results. If it is above or below this point, then my results will not be correct. And the next way of determining the modulus of elasticity is, I am choosing a point somewhere here and I am drawing a line to the origin point, and if the modulus of elasticity is measured with respect to the slope of this line, then it is called as secant modulus, and this secant modulus will give more or less the approximate value of modulus of elasticity of concrete, and this secant modulus is being used widely to determine the modulus of elasticity. If suppose a line if being drawn between the two chord points, if the modulus of elasticity is found out between any 2 points joining the chord. If the modulus of elasticity is determined with respect to the chord which is drawn between any 2 specified points, then that modulus is referred to as chord modulus. So, this is why we stated that the modulus of elasticity for concrete can be measured in different ways, and this secant modulus is the one which gives the approximate values of modulus of elasticity for a concrete. Now, the factors affecting the modulus of elasticity. What are the factors that affects the modulus of elasticity? What are the factors that affects the modulus of elasticity? Again, I am plotting stress strain graph. Cement paste stress strain graph this is, and this denotes for the concrete and this is for aggregate. So, the stress strain curve for a cement paste is somewhat low, and that for when compared, the stress strain curve for cement paste is low when compared to that of the aggregate, and aggregate is the one which is having higher stress strain value, and concrete, which is a mixture of both the cement paste and aggregate, exhibits a stress strain curve in between the stress strain curves of aggregate and cement paste. The reason why the concrete exhibits a value, stress strain value lesser than that of the aggregate is because of the micro cracks that arise between the aggregate and the cement paste, which we discussed in the last lecture, that is the interfacial transition zone, ITZ porosity. Because of that reason, we are exhibiting the stress strain value of concrete lower than that of the aggregate, and also the non-linearity of the stress strain curve is largely related to the micro cracking. That is, when a crack is being formed, then at that time when we are applying stress, the strain will form in a greater manner when compared to that of the stress, and that's the reason why we are getting a curve in a non-linear manner. And this modulus of elasticity of concrete is a function of modulus of elasticity of paste and aggregate, and this modulus of elasticity of aggregate will tend to give higher value that is the higher modulus of elasticity of aggregate will tend to give higher modulus of elasticity of concrete. And next is wet specimens exhibit higher modulus of elasticity. If suppose my specimen is wet, then that time I will be getting higher modulus of elasticity value. But how it's that possible? When talking about the strength, we discussed that the dry specimen will give higher strength when compared to that of the wet specimen. Then how come here the wet specimen will give me higher modulus of elasticity? This is the reason behind this is, in wet specimen all pores will be filled with water. So at that time, if I am applying the stress, my strain will not be in such a large varying manner. Since all the pores are being filled with water, it exhibits lesser strain when compared with that of the dry specimen. Since in dry specimen the pores will be empty, that is, all the pores might not be filled with water. So at that time, if I apply stress, my strain behavior will be in a different manner. Now we are going to discuss about creep. What do you mean by creep? Creep is nothing but, what do you mean by creep? It is a tendency of a solid material to move or deform permanently under the influence of stresses. Why the deformation occurs? It is due to the sustained loading. Creep, it is a tendency of a solid material to move or deform permanently under the influence of stresses, and it occurs due to the long-term exposure of the stresses, and that stress values will be below the strength of the stress values, the stress which is being maintained for the long period, that stress value will be below the stress values will be below the ultimate strength of the material. And this creep occurs in metals, polymers, and of course in concrete. And this and the creep that occurs in concrete is different when compared to the others. So again I am drawing, this is a stress and this is the age. As per the definition, creep occurs due to the sustained stress, that is, the permanent deformation occurs due to the long-term exposure of the stresses. This is 0 and this is sigma naught. This is the stress. This is T naught. If suppose I am applying a stress sigma naught at age T naught and I am maintaining it for a certain period, say till at the age of T. Now for this, how my concrete behaves is being shown here. This is sustained stress, and because of this sustained stress, how come that permanent deformation or movement is occurring in my concrete? Because of the sustained stress. Again, this is age and this is strain. Because of the stress, initially I will be getting some initial elastic strain at the age T0, that is after the application, during the application of the stress, I will be getting some initial elastic strain, and after that I am maintaining the stress for a certain time period, and during that time period what strain I am exhibiting here, and this is E0, and during that sustained loading period my strain value changes like this. That is at HT my strain value is ET. This is my initial elastic strain. That is, during the application of stress sigma naught, I will be getting this initial elastic strain, and after maintaining the stress for a certain period of time, my strain value changes like this, and this difference is called creep after time T minus T0 is nothing but ET minus E0. Because of that sustained loading, this is the behavior change in my concrete, and that behavior change is termed as creep after a particular period of time. Here we can find two components. One is the initial elastic strain, and another is the and with respect to time there is an asymptotic curve, and the difference between these two is termed as creep. Now I am plotting this stress and strain in the same graph. Here I have plot for age, that is a period of loading, stress different in a different curve and strain in another different graph. Here I am plotting both stress and strain in the same graph. Because of this sigma naught, I will be getting this initial elastic strain, so that I am plotting here. And after a sustained loading, say after a sustained load after 7 days or 28 days, I will be getting the strain value in this manner. This is the due to this strain value is because of this initial application of stress. So, initial elastic strain that is E naught and here ET, and this is called creep. Because of this initial stress, I will be getting one initial elastic strain, and after maintaining the same stress for a certain period of time or age, that is after 7, 14 or 28 days, there is an increase in the strain, and that difference is called as creep. Mechanism of creep. The exact mechanism of creep is unclear to till date. It is somewhat related to gel and gel pore system. It is somewhat related to gel and gel pores. It is related to gel water and pore system of concrete. Related to gel and gel water and pore system of concrete. If in a concrete, if all the evaporable water has been removed, then that concrete will exhibit little creep when compared to that of a wet specimen. If a fully saturated sample is being kept, then there will not be any movement of water, since the creep is mainly related to gel water movement. If a fully saturated specimen is being kept, then there will not be any movement of water. So, when compared to that of a saturated specimen, the dry specimen, that is after removing all the evaporable water, we can exhibit a little creep in the concrete, and this creep occurs within the at all stress levels within the service stress of the concrete, that is without exceeding the ultimate strength of concrete, and within that ultimate strength of concrete, this creep occurs at all stress levels. Next, is the factors influencing creep. What are the factors which influences the creep? First one is modulus of elasticity of aggregate, water cement ratio, curing condition, relative humidity, volume to surface area ratio, fine aggregate, coarse aggregate volume and air content. Now we'll discuss about these each factors. First one is modulus of elasticity of aggregate. This is the modulus of elasticity of aggregate, and this is the relative creep. This is in GPa. Let us assume 40, 60, 80, 120. Red sandstone, green sandstone, river gravel, granite, basalt. From this graph, we can tell that the higher modulus of elasticity, with the aggregate which is exhibiting higher modulus of elasticity has a less creep when compared to that of lower modulus of elasticity of aggregates. Higher modulus of elasticity of aggregate exhibits lesser creep. The cement paste is responsible for this creep. So, when a higher modulus elasticity of aggregate is used, it doesn't allow the cement paste to creep in a faster rate, and that's the reason why the higher modulus of elasticity of aggregate exhibits lesser creep. Water cement ratio and age of loading. Age of loading. Seven, 14, 28. Water cement ratio. Higher water cement ratio means more pores, then there is a likelihood for a larger creep. If lower water cement ratio, then less pores, and it results in less creep when compared to that of higher water cement ratio. This higher and lower water cement ratio are mainly related to porosity and if the age of loading increases, then the creep value decreases. and this higher water cement ratio means there is a likelihood that all the gel pores might not be filled with water, so there will be a high movement of water from gel pores, so that exhibits a more creep, whereas in lower water cement ratio there will not be many pores as compared to that of higher water cement ratio, and the creep action will be somewhat low when compared to this. Next is relative humidity. This is the creep value, and this is the time since loading, 28 days, 90, 1 year, 2 year, 3 year, 10 year, 50, 400, 1,200, $50, $70, $100%. This is when the relative humidity, the time of loading and the creep, a graph is plotted between the two, taking the relative humidity as the main factor. If suppose my specimen is having only 50% relative humidity, then it exhibits a larger creep when compared to that of a 100% specimen having, when compared to that of the specimen having 100% relative humidity. If the reason behind is, in 100% relative humidity, all the gel pores will be filled with water, that is the adsorbed water. There will not be any movement of water between the gel pores, and that's the reason why the 100% relative humidity specimen is exhibiting a less creep value when compared to that of the 50% and 70% relative humidity specimen. Next one is volume to surface area ratio. Volume to surface area ratio. This is the ratio of 30-year creep. $50, $100, $150. if the volume to surface area is more, then the creep will be low. More volume to surface area, less creep. And if the volume to surface area ratio is low, then it exhibits higher creep when compared to that of the high volume to surface area ratio. If suppose the more volume to surface area, why it exhibits less creep is the surface area meant for evaporation is less when compared to that of the low volume to surface area ratio. Here the surface area will be more and there the evaporation take place, that is the absorbed water will get evaporated, and because of that there will be movement of gel water from pores, and that's the reason why the less volume to surface area ratio exhibits higher creep when compared to that of the high volume to surface area ratio. Next is temperature. Relative creep, and this is temperature in degrees Celsius. If suppose I am curing the concrete at 20 degrees Celsius, I am curing the concrete at the test temperature, that is the 20 degrees Celsius, and applying load, then it shows a pattern like this. But if suppose I am curing the concrete at 20 degrees Celsius and if I am heating it to 40, 60 or 80 degrees Celsius, and that time I will be exhibiting creep in this manner. Here this curve, how I am obtaining is cured and tested at the same temperature, that is I am curing at 20 degrees Celsius and I am applying the loading at the same 20 degrees Celsius, whereas here I am curing it at 20 degrees Celsius and before loading I am heating the specimen to different, and I am heating the specimen to the test temperature, whatever it may be, 40 degree or 60 degree, and before loading and after heating I am applying load, and during that time I am exhibiting a creep in this manner. Here if I am curing and I am applying load at 40 degrees Celsius, then my creep will be somewhat in this manner. At 60 degree it will be here, and nearing 80 I am having a drop in my curve. This is due to the reason that all the evaporable water, that is, since I am nearing 100 degrees Celsius, all my water in the system has been evaporated and there will not be any further movement, and that time I am exhibiting a lesser creep. Whereas here I am curing at one temperature, and before applying load I am heating it to the test temperature, and because of that variation I will be having movement in the gel water system, and so I am exhibiting a higher creep.